Hello and welcome to the Consilium Aquis Sulis Introduction to Train Protection, part of our series on train protection and automation. This course is intended for transportation engineers, operators, consultants, and managers, and consists of a single online video presentation, which can be viewed at will. Please note that the course is for educational purposes only. Please consult the applicable standards for definitive information. There are no prerequisites for attending this course. This video will answer the question, what are train protection systems? It will then describe different types of train protection system, starting with warning systems, followed by train stops and speed traps. Finally, it will explain the comprehensive speed supervision provided by automatic train protection. Train protection systems are technologies that mitigate the risk of driver error leading to a train traveling further or faster than authorized. Traveling further than authorized is known as an overrun, whereas traveling faster than authorized is known as an overspeed. Where necessary, train protection systems intervene by automatically cutting train traction power and applying the brakes. Such interventions may be preceded by a warning to alert drivers to the need to slow down. The extent to which the risk of overrun or overspeed due to driver error is mitigated depends on the specific train protection technology and scenario. Effective mitigation may also be dependent on the correct configuration of the technology, with parameters representing train and infrastructure. Furthermore, there are causes of overrun-overspeed risk that a train protection system cannot mitigate, such as the signaling system issuing an incorrect movement authority to a train, failure of a train's braking system, and poor wheel rail adhesion. It is also worth noting that train protection is only one possible mitigation for overrun-overspeed risk. Others include the safety integrity of the signaling system issuing movement authorities to trains, the logical conditions for issuing those movement authorities, safe overrun distances reserved beyond the end of movement authorities in which a train can stop without colliding with other vehicles, signaling controls to slow trains down at critical locations, the safety, integrity, and performance of train braking systems, safety margins in train braking calculations, measures to mitigate the risk of low adhesion such as vegetation clearance, spraying of sandite and sandboxes on board trains, forecasting and reporting areas of low adhesion so that drivers can adjust their driving style appropriately, driver competence and route knowledge, defensive driving policies that encourage drivers to brake early for ends of movement authorities and speed restrictions, signage to remind drivers of permissible speeds. Warning systems are a very basic form of train protection, whose primary role is to alert drivers to operational restrictions that may require them to apply brakes or take other action. Typically, these restrictions are signals displaying restrictive aspects, indicating the end of a train's movement authority, stop boards, and buffer stops. They may also include warnings of reductions in permissible speed. A warning system may apply brakes if a driver fails to acknowledge a warning in a defined period of time. One example of such a warning system is the Automatic Warning System, AWS, used on mainline railways in the UK. AWS transmits its warning to trains via magnetic fields. As a minimum, trackside AWS equipment consists of a permanent magnet. If a train reads just the field transmitted by that permanent magnet, then a warning indication is displayed in the driver's cab, and a horn sounded, which the driver must acknowledge to avoid a brake intervention. The permanent magnet may be followed by an electromagnet of the opposite polarity, which, when energized, indicates that the next signal is displaying an unrestricted proceed aspect. A bell sounds in the driver's cab, which does not require acknowledgement, and any previous warning indication is removed. The French crocodile warning system functions in a similar manner to AWS, but communicates via electrical potential rather than magnetic fields. A metal bar between the rails is energized at a specific potential relative to the rails to indicate whether the next signal is displaying a restrictive aspect or not. Passing trains measure the potential difference between this bar and the rails by means of a metal brush underneath them. The German Induci and Spanish as FA technologies achieve similar functionality using tuned circuits. Passing trains transmit electromagnetic radiation at specific frequencies, which causes tuned circuits in trackside equipment to resonate. The tuned circuits consist of inductors, capacitors, and resistors that can be switched according to signal aspect. Resonance at specific frequencies is detected by equipment on board the trains. A further means of communicating with passing trains is coded track circuits, as used by the Irish Continuous Automatic Warning System. An alternating electric potential is applied between the two rails, which is detected by passing trains. This alternating potential is itself modulated to communicate signaling states to trains. Whereas warning systems warn drivers that they are approaching the end of a movement authority, train stops intervene by applying brakes and cutting traction power if they pass it. Train stops are usually found at signals capable of displaying red aspects and accompanied by safe overrun distances, in which trains can safely come to a standstill after brake application on passing a red aspect. The earliest type of train stop used a track-mounted mechanical arm that, when raised, pushed a train-mounted tripcock on passing trains. When thus activated, the tripcock instigated a brake activation, bringing the train to a standstill. Train stop functionality can also be achieved electronically, for example by Induci and ASFA circuits, the resonated frequencies corresponding to stop aspects, or by track-mounted pairs of inductive loops transmitting alternating magnetic field at specific frequencies, as used by the train stop system in the UK Train Protection and Warning System. Alternatively, track-mounted beacons or balises can transmit electronic messages instructing brake activation. These are used by a range of train protection technologies, including ETCS, KVB, SCMT, and TBL. Whereas train stops, when active, always trigger a brake intervention, speed traps only trigger a brake intervention if passed above a specific set speed. For example, the UK TPWS Overspeed Sensor System OSS provides speed trap functionality, using track-mounted pairs of inductive loops transmitting alternating magnetic fields of specific frequencies, different to those of TSS loops. OSS loops are separated by a configurable distance. The first OSS loop in the direction of travel is known as the arming loop, which, when energized, causes a timer to start on board passing trains. If the train reads the second loop, the trigger loop, before the timer has expired, then brakes are applied. The intervention set speed of an OSS is thus dependent both on the distance between the loops and the duration of the onboard timer, which can be different for different types of train. Speed traps can be used to complement train stops. A limitation of train stops is that trains traveling above a certain speed may fail to come to a standstill in the safe overrun distance after a brake intervention at the train stop. A speed trap set to this speed on the approach to the train stop can greatly reduce the likelihood of such trains reaching the train stop by applying a brake intervention earlier. Train stops can even be configured to act as a speed trap themselves. This is achieved by configuring a train stop to remain active until a train has been detected in an approaching section of track for a specific time. If the train passes through the section of track in less than this time, indicating that it is traveling above the set speed, the train stop applies brakes. An even higher level of protection can be achieved by continuously supervising train speed, as is done by automatic train protection (ATP) technologies such as ETCS, KVB, LZB, SCMT, TBL, and TVM. As well as intervening if trains exceed the limits of their movement authorities, ATP also supervises the braking curves on the approach to those limits. Many ATP technologies rely on intermittent transmission, whereby ATP information is only transmitted at specific locations, generally by means of track-mounted beacons or balises that only transmit information to trains passing over them. A limitation of intermittent ATP technologies is that they can be overly restricted when a signal steps up to a less restrictive aspect. A driver may see the new aspect, but be unable to accelerate until the ATP has received updated information from a beacon or balise associated with the signal. Similarly, if a signal steps down to a more restrictive aspect, ATP will not supervise the new aspect until the train passes the associated beacon or balise. Before this, reliance is placed on the driver seeing and responding to the aspect. ATP with continuous transmission overcomes these limitations by continually providing train-borne equipment with updated information. Various media can be used to continuously communicate ATP information, including coded track circuits, continuous inductive loops, leaky feeder cables, and radio. Radio tends to be preferred in modern continuous ATP systems as it entails less track-mounted equipment. In summary, train protection systems are technologies that mitigate the risk of driver error, leading to a train traveling further or faster than authorized, intervening where necessary by cutting traction power and applying brakes. Warning systems are a very basic form of train protection, whose primarily role is to alert drivers to operational restrictions that may require them to apply brakes or take other action. Whereas warning systems warn drivers that they are approaching the end of a movement, authority train stops intervene by applying brakes and cutting traction power if they pass it. Speed traps apply brakes if a train is traveling above a specific speed and are sometimes used in conjunction with train stops. Automatic train protection, ATP, systems achieve a higher level of protection by continually supervising train speed, including braking curves.